Okay, so far in this session, what we have covered is defining graph neural networks that are basically relation specific. They handle different types of relations. Relation aware. So they handle different type of relations that are defined on the graphs, and they can learn based on multi-relational graphs or heterogeneous graphs and so on and so forth. So now what we want to do is that we want to train these models. To train these models, we discussed the encoder now. In the previous session, we discussed different type of decoders that we can have. And as a reminder, we said that for multi-relational graphs, what we do is that during reconstruction, we assume that we're just reconstructing the existence of different types. So previously for node-node relations, we were learning based off of different types of node-node similarity measures, but for multi-relational graphs, because it's going to be more complicated, we just simply use the adjacency tensors. We want to replicate, we want to reconstruct. So now what is left is loss function. To train these models, we in general have three types of loss functions.
Why do you want to define a decoder?
What was that?
I didn't understand why do you want to define a decoder?
Why I want to define a decoder. So we said that to learn, you remember the in session 8, I think, we went over the shallow embedding approaches, and we said that we want to define an encoder decoder type of framework. So we're basically basing our conversation on that.
You're reducing the dimensions of your.
Again, yes. So we want to learn some embeddings that the decoder using those embeddings can reconstruct the multi-relational neighborhood. So we want those embeddings to be meaningful in order for our decoder to be able to use them to essentially predict if the edge between those entities, head and tail, exists of relation type tau. So that's the idea, and we went over 6 different types of decoders last time, and in many literature you can see that this model is one that people choose for baselining. But now we don't want to discuss about that. We want to focus on defining the loss function. So there are 3 types of loss functions in general that are used for training essentially learning embeddings for multi-relational graphs. The first one is reconstruction loss, which simply tries to reconstruct the adjacency tensor given the prediction for all the edges between every pair of entities. The other example, basically approach is cross-entropy loss, which is basically trying to maximize the probability of seeing the data, observing the data in the hand. And the last approach is max margin, which is similar to cross-entropy in the fact that it compares the score given to us. It wants to maximize the plausibility of the essentially data in hand, observed data, but with the difference that it does not use probabilities. And we will go in details and see what they do. So first of all, we start with the reconstruction loss. In this approach, what we do is that we say that our decoder, FD, is predicting how plausible is that a relation tau is between 2 basically entities, VH and VT. So we get this plausibility score and we want to maximize it. We want to, using that, reconstruct our adjacency tensor. And when we say adjacency tensor, it is because it is multi-relational. So it is a tensor of V by V. And then we have tau total number of types on this graph. So it's a tensor of V by tau, basically the total number of taus, which we are showing with the set of them we are showing with calligraphic art. Now, there are two problems with this. Essentially, this type of MSE, mean squared error type of relation that we defined here. The first one is the computational cost. And the second one is that the nature of the task is basically not compatible with MSE. Now, let's take a look at the first one. We see here that we have all different types. We have an adjacency matrix, and what we want to do is go over all the nodes, all the basically pairs of entities that we have. We go over all the types of edges that we have, and we want to reconstruct, we want to see if they exist or not. We want to predict this. So the amount of operations that are needed is order of V squared times R. But this is very expensive, and in many cases, it is not necessary. So what this means is that this would be necessary when you have every type of relation between every entity out there in our graph. But that's usually not the case, and our graphs are usually sparse. So this adjacency tensor A is usually sparse. So many of the operations that we have are just waste of time. So the total number of the edges is usually way smaller than this V squared R. So we would ideally want to define a loss function that only uses order of E operations to compute the loss. So this is a wasteful loss, and that's number one issue with it. The second problem is that many of our graphs are just binary. I mean, the relation types are discrete, meaning that adjacency tensor is binary. So for each essentially pair of nodes, a pair of entities, we either have 0 or 1 for different type of edge that can possibly be there. So this is essentially a classification problem where you want to classify which edge type is there between two different entities. And the MSE loss that you're using is more natural to training regression models. So although you can, technically speaking, numerically, you would be able to train this using MSE, it is not of the same nature that we would want. So it is better to use something more natural to a classification problem. And with that, we can use cross entropy loss as our loss function. So here, for training multi-relational basically models, we can use cross entropy with negative sampling. What that means is that we want to, given a basically set of information, set of nodes and relations between them, we want to maximize the probability of observing the data in hand. And then we want to also minimize the probability of the data we are not seeing. That's the negative sampling part. So we construct some edges that do not exist with some relation types between them. That edge does not exist, and we call that a corrupted edge or a corrupted, essentially, triplet. So now what we do is that we want to solve a binary classification problem given each triplet. We want to say that if this triplet is basically there, do we observe that? Or do we not observe that? So these are basically two scenarios that we want to classify for. So we can write our probability that we want to essentially maximize as probability of basically seeing the triplet that we have in the data. So let's define this. If we have a pair of entities, VH and VT, and these are related by some relation tau, right? So if this is in our data set, we call the event D1, the event that this is true, and we call event D equals 0, the event that this is not true, meaning that there is no relation of type tau between entities VT and VH. So I can write my probability that I want to maximize as multiplication of all these, right? So I write it as probability of event 1 for the data in the training set and probability of event 0 for some corrupted edges that I have created. So here we say that we sample some Vn from the set of all the nodes in the graph. And by corrupting, I mean that I take the tail of my relation and I put it instead on that node that I just sampled. And that way I create basically a corrupted edge. And I will basically go over that again in a few slides. So we said that we want probabilities and we're solving a binary classification. So what we can use to get this is a sigmoid function. So redefine it, we basically recall that sigmoid function was getting x from -infinity to +infinity and was returning a value between 0 and 1. So it was rescaling this between 0 and 1 so that our output now is a probability value, right? So I can use that. I can take our score given by my decoder and I can plug that into our essentially sigmoid function. And that will give me a value between 0 and 1 that I can use to represent the probability of observing that triplet. So now I again write down my basically objective function. I can say that the probability of event 0 is 1 minus probability of event 1, right? Because it's only 2 scenarios and some of them are equal to 1. And then we said that we use a sigmoid function of the decoder in order to represent that probability of event 1. So now I take that and I can, instead of maximizing this, I can minimize this by applying negative log. It is numerically more stable. If we don't have this basically this product here, this minimizing this loss function now is more numerically stable. So we turn this product now into sum of logs of these two terms, right? And we note that for the sigmoid function, this identity basically we can use. It is 1 minus the sigmoid of something, x, is equal to sigmoid function of the negative of that value. So I can use that. I can plug this identity. I can use that identity here in this equation in the log of the sum, and then I can rewrite that as log of sigmoid of negative of the score given by my decoder, right? So now, using that, I can define my loss function. This is only for one edge, right? For one edge, I'm given these entities, embeddings, and the relation type, and I sample some essentially negative samples, and I compute the loss for only this edge. And then if I wanted to have the loss for the whole graph, I need to perform this over all the edges in my multi-relational graph, right? So that's essentially it. And I can write this Vn as basically a node that is sampled from basically from all the nodes that I have on the graph. So I can represent this using PV, where PV just means some distribution over the nodes of the graph. Now, I want to, again, just show how this negative sampling works. Let's say that I want to, I have this graph. I have three different relation types here, and these are directed edges. So let's say that take this edge 5, 4, for instance, right? And I want to compute the loss over this. So I take this and I say that I want to generate negative samples. So generating negative samples means that I'm keeping this head and changing the place of the tail. So I put it here instead of there, and this is a negative sample, meaning that it starts from the same node as this positive sample, but its end is just some random wrong place. So this is called true edge. This is called corrupted edge. Now, there is one issue, and that's the fact that we said that we are corrupting the edge by replacing the tail entity with some randomly selected node on the graph. And that will generate some directional bias because every time we're just changing the place of tail. So what we should do, what is better to do is that also change the place of head as well, but don't do them at the same time. So when you try to corrupt some edge, you either change the place of head or you change the place of tail and not both of them at the same time. So I can define the set of corrupted edges for, let's say, some. So I can basically generate corrupted edges with two approaches. Either I take this VH and keep it, and I change the place of the tail, and I swap that with some randomly sampled node, or I keep the place of head and tail, and I swap the basically head entity with some randomly selected edge in the, this randomly sampled node in the graph. Now, so there is another issue too. Another thing that we should just keep in mind is that here, let's say that I have relations starting from 5 ending at 4 of type magenta. Let's say that I have randomly selected this node, and then I see that I actually have an edge of type magenta between 5 and 6. So this is a false negative sample. We have randomly basically selected a node, connected it to our head entity, and we wanted to have a corrupted edge, but what we have actually is some actual edge that is in the graph. So we don't want to do that. It doesn't often all the time because, you know, there are a large number of nodes in the graph, but it can happen. So in order to alleviate that, what we can do is to impose some filtering approach where if basically after you select your randomly selected the node and then you constructed the corrupted edge, what happens is that this filtering filters out any false negatives. And then after doing that, we use Monte Carlo approach to compute the sum over all the negative samples and then to compute our loss. So the last type of loss that we can use for training over multi-relational embeddings is max margin loss. So it is similar to the cross entropy loss in the fact that this is dealing with comparing essentially negative samples and positive samples. But the difference is that this is using the direct score given by the decoder instead of turning it into a probability. Mathematically put, we are computing the max of 0 and the difference between the output of the negative edge and the output of the positive edge plus some margin. So this margin is some parameter. And the idea with this basically type of implementation is that we want the different output of the decoder for the positive node be larger than the score that this decoder gives to the wrong samples, to the corrupted edges. And we want that to be larger at least by a margin delta. All right, so three types of losses. Let's go over a summary of what we have covered today. We essentially today we talked about multi-relational graph neural networks. There were two types of implementations that we discussed. The first one was relational GCNs, which were essentially redefining the GCNs by essentially defining relation-specific parameters or matrices to update update basically our embeddings. Then the problem with these approaches was that they're very expensive. If you want to define weights, parameters for all the matrices, all the relation types in your problem. Now, what you can do to improve that is twofold. You can either use basis decomposition, where we essentially using a fewer number of the basis matrices of the same dimension of the W, but way fewer than the total number of the edge types that we have in the graph. And then we have a vector for each edge type, only a vector that shows the combination of the essentially shared matrices, the basis matrices, that the linear combination of these that will result in the essentially relation-specific weight for that edge type. A second approach that we discussed was concatenation-based approaches, in which we say that we might not have different types of edges, but we might have different basically vector value, basically real valued vectors associated with different edges. So in this type, we can't associate a different weight essentially to each edge type. What we do is to concatenate the embedding of the edge with the essentially tail entity of, or basically the neighboring entity of each node. And then we collect, when we aggregate the concatenated vectors of edge embedding and node embedding of the neighboring node. The last thing that we discussed today was different type of losses that we can use to train multi-relational embedding approaches. The first one was reconstruction loss, which was expensive. It most likely will have an unnecessary number of operations to train our model. And the second issue with that was that it was based off of mean squared error, which is not natural to many basically graphs that are defined using discrete essentially edge types. Then we went over cross entropy and defining essentially negative samples by corrupting the essentially head or tail of an edge and basically an edge between two entities. And then we looked at max margin loss, which is essentially trying to impose the constraint that your decoder's score for the true edge must be larger than your score for the negative edge by some margin delta.